from not too far away, down in the stats department. And he's going to tell us about post-Bayesian machine learning, a lot of the pre or current in Bayesian time. Let's see what post is.
Sorry, I am trying. Can't see my mouse for some reason. 1 second.
Oh, but actually, no, this would all see it.
Oh, of course.
Well, you probably want to get rid of it on yours too.
Yeah. Okay, fantastic. Well, thank you everybody for coming indoors when the weather is so lovely. I really appreciate it. And I feel quite honored to be in these, in these halls today. I would say the Gatsby is like one of the temples of Bayesian machine learning. So I hope I'm not committing sacrilege today. But what I'm going to try and present to you is sort of the work that I've been undertaking over the last 5 to 8 years. And I've called it post-Bayesian machine learning because a lot of the pitch today will be about moving past Bayes' theorem as the singular device upon which we rely for building inference procedures that have Bayesian characteristics. So obviously, before we start tearing down the house, we should have a look at what Bayes' theorem looks like. I'm sure you're all familiar with it. It's basically just a mathematical truth, and we're not going to try to argue against that. It's a mathematical truth about how you can invert conditional probabilities. But what we will worry about today is the way we use this inversion in practice. So when we do Bayesian machine learning or Bayesian statistics, what we do is we translate this mathematical theorem into a device for data analysis, and we do so by positing a conditional model on your data, which depends on a parameter that I've denoted theta here. And then we're also forced to place a prior on that parameter in form of a probability measure. And then when we invert the probabilities, we arrive at the reverse conditional, which is the parameter given the data, and that's the Bayes posterior. And this has 3 great advantages. It allows you to average over models. So hopefully you'd be robust against choosing a singular model that perhaps doesn't describe your data that well. It quantifies your uncertainty in that sense. So it allocates probability mass to regions of the parameter space that you think are well suited for describing the data you've observed, instead of picking a singular value, and also allows you to include prior probability, which is a much advertised feature of this way of looking at the world. And sort of like a simple example, or maybe not so simple, but a very popular example would be Gaussian process regression. So you can see here, the sort of red bands describe your uncertainty. In this case, 95% quantiles. And so basically what you're trying to do is you're trying to figure out where the true function lies. And as you observe more and more data by repeatedly applying this operation, you can narrow down your uncertainty about the true function. And Bayesian inference, obviously has a very long and checkered history. It's more than 250 years old, really. And it obviously starts with Bayes' theorem itself, even though the French would probably argue there should be called Laplace theorem, but we're not going to get into that today. And then in the mid-1900s, you get a lot of innovations that really solidify the idea of using this as an inferential device. And there's lots of important mathematical results that we will revisit in a bit. But the thing is, up until now, it's not really something you use in practice. It's sort of like nice conceptually, but it's not before the 60s and 70s that people develop really, in principle, tools that will allow you to actually compute with these objects. And really in the 80s and 90s is when, for the first time, the computation becomes really feasible on a mass scale. I'm not saying it wasn't happening before that, but that's really when this becomes more mainstream. And what simultaneously happens in machine learning, starting in the 1990s, really is that machine learning becomes increasingly data-centric. And so this nice marriage and confluence of 2 independent streams of research comes together and forms Bayesian machine learning, which is, in the classical sense, what we're familiar with. I'm not going to talk about the sort of classical perspective. What I'm going to talk about today is sort of what happens afterwards, from the 2000s onwards, which I would argue you could describe as a sort of post-Bayesian movement. So these are algorithms that take Bayesian characteristics, but don't rely on the inversion of probabilities. And that's what today's talk is going to be about. So in a nutshell, today's talk has basically 3 parts, the first of which we've just covered, right? I've pitched to you why Bayesian machine learning is something you should care about. You average over models, you quantify your uncertainty, and you can include prior probabilities that sort of reflect your expert judgment. That's all good and nice. And in the next part, I'll sort of briefly walk you through, what the problem is with this in the context of machine learning and why perhaps we should be a bit cautious about naively applying Bayesian machine learning. And then in the last part, I'll kind of explain what one of the potential remedies to this issue is, and that's post-Bayesian machine learning. Okay, so, before, again, we tear the house down, let's look at these foundations again. So when I started working on this, It wasn't particularly fashionable, it's fair to say, I think. So I submitted a paper in 2018, and one of the reviewers had a look at it and said, the base posterior is principled and grounded in foundational work of De Finetti, Savage, and Birnbaum, as well as others. This work gives up these guarantees and provides very little in return. So that's true, right? There are definitely foundations that explain to us why Bayes' rule is a good idea as an inferential device. But what often is sort of glossed over is what kind of assumptions you actually need for these foundations to be meaningful. And these foundations are really the critical element that I will argue are what makes this somewhat infeasible in practice quite often. So one of those is the assumption that the model is correctly specified, which means that for one of the parameters in your parameter space, you can actually recover the model correctly. And the reason this is important is because it basically means that the parameter space is the only relevant state of the world you then need to care about for decision-making and for forming your beliefs. The second assumption is somewhat related to this, and it relates to the prior. And it tells you that your uncertainty about the true state of the world should be expressed in your prior, which is possible because the parameter space is an accurate representation of at least the part of the world you care about. And it forces you to essentially elicit your own uncertainty about the true state of the world and write it down in a probability distribution. Of course.
So, no, expert, might be here forever. But we're constantly building models and we know we're wrong. How does that square with the first one?
Yes. That's part of the problem. Yeah. So obviously, right, this never holds completely, but there's a difference between at least trying to build a model that, to the best of your knowledge and the best of your beliefs or the beliefs within your field, reflects the data generating mechanism versus using, let's say, a model that's just Gaussian, even though you know the tails are quite heavy. There's a difference between those two. So if you're still trying your best, I think you probably get off, right? Nobody would try to hammer you on the cross for that. But yeah. You're not alone. There's quite a lot of those people. We will talk about that later, I think. So you have these two assumptions, and then the third one that often isn't mentioned explicitly, but I think is actually quite important, is that you can actually work with the outcome. So once you've written down these conditional and unconditional probabilities, you can actually perform the inversion. Otherwise, none of this is particularly useful in practice. And so the problem with all of this is actually quite fragile. And so what I'm going to do next is I'll walk you through an example, sort of worked example, which relates to the Boston housing data set, which some of you may be familiar with. It's sort of one of the canonical UCI data sets. And I'm going to use that to contrast why these assumptions were useful in sort of classical Bayesian analysis and classical Bayesian statistics, but why perhaps they are not necessarily feasible for Bayesian machine learning. So in classical statistics, right, in Stats 101, you sit down. Basically, the view of the world you get taught is there's an expert scientist, and they have a research question, and they collected some data, and that data is probably handcrafted for that specific problem that they were trying to solve. Then they sit down, they write down a model that's based on sort of their best belief about the world, as we just discussed. And they read the literature and they come out with a prior belief about the parameters in the model, all of which are probably interpretable and have some meaning in the world that they can understand. And then all you do is basically computation. And the computation here isn't the interesting thing. It's more sort of a side effect of the procedure. And this is, in fact, exactly the sort of situation you find when you look at the paper that actually collected this data set, the Boston housing data set. It was collected in the late 70s by two economists who were wondering, what are people willing to pay for an improvement in the air quality in terms of their housing prices? Okay. And so what they did is they came up with this carefully specified model, a lot of which is based on economic theory. So we can get into the weeds of whether economic theory is a good idea, right? But, yeah, exactly. But at least to the best of their abilities, they put in the effort of specifying a model that was very much specific to the data set and the research question they had in mind. And this model, if you read the paper, it's actually quite interesting. There are obviously parameters of interest that tell you about the phenomenon you want to study, and then there are parameters that you need to control for in order to not bias the parameters you actually want to find out about. Similarly, the priors are sort of handcrafted and fine-tuned by these researchers, and so the computation also isn't particularly difficult because this is just a linear model. So in this instance, you can see that all of these assumptions, they're fine, like they're not dramatically violated, at least not in an obvious way. If you contrast this with how we use this particular data set, or any data set really in Bayesian machine learning, it's really different. In Bayesian machine learning, at least how it's practiced today, you really start with the model first, probably the prior as well. So already you're not handcrafting that to any particular data set. And instead, the sort of goal is that you can throw this at lots of different data sets and it works anyways. And that also means you need a very flexible model. And so computation becomes a much more important part of this. Like your computation is usually specific to the model that you've posited to begin with. And so an example, I've picked one, I could have probably picked a million other ones, but there's a 2020 paper from Tim Pierce. And basically the research question here is fairly generic. It's, we have this new Bayesian deep learning algorithm. We apply it to a bunch of data sets that are regression tasks. Does this perform well? So the model that they specify is obviously, you know, a neural network, which is not misspecified because it can probably capture most data generating processes. So that's not really the issue here. However, because it has so many parameters and you don't really know what kind of priors to specify on these parameters, because essentially they're all incidental. You really care about the function. You don't really care about the parameters here. What they end up doing is taking a prior that allows them to compute the thing, right? So it's just a Gaussian prior. So that's definitely not sort of a carefully tuned prior probability distribution that reflects their beliefs about the world. And then similarly, to compute the posterior, even though they've already chosen the prior for computational convenience, they can't actually do it. So they still need to approximate it. So this is very different from that, I think we can all agree. And so this leads to the fact that the assumptions you need to make Bayesian inference work, really, they're somewhat fragile in Bayesian inference.
Which one works better?
Sorry?
Which one works better on the stats? I mean, Bayesian is actually improved.
I'm not sure I understand the question.
Well, I mean, so the economists have their model, the Bayesians have their model.
Oh, right. Well, so
You can't answer that, right?
no, you can't answer that because actually they ask different questions, right? So the economists here, they were interested in a very specific question. So they're actually even looking at a transformation of the raw data anyways. So this Y that they're regressing things on isn't even just like the price, it's something else. It's trying to capture the marginal increase in price, given it's basically a derivative, given the increase in air pollution. So they're not even trying to answer the same question. That's kind of part of my point.
Really could apply their model to this Y.
I'm sure you could. I haven't checked whether someone has done that. Yeah. Maybe it's better in terms of the predictive error, right? But my point here is just that the tasks you're setting up they're very different tasks. If you purely care about prediction, I'm not arguing this is better. I'm just saying the assumptions that you need to make sense of the Bayesian workflow, they're satisfied in this case, they're not satisfied in this case. Okay, and so to summarize this, I really like this paper by Drovandi, which when he originally put it on arXiv was called On the Brittleness of Bayesian Inference. They since had to rename it. I'm pretty sure an editor wasn't happy with the name, but I quite like the name. And to read to you from it, it says that Bayesian inference is generically ill-posed with two arbitrarily close models and data one may reach diametrically opposite conclusions, and any given prior model can be slightly perturbed to achieve any desired posterior. There's some very heavy math in there, so this is not just a vapid claim. If this is thought-provoking to you, I recommend you take a look at the paper. It's really interesting. Sorry?
Consider good or bad.
And to sort of give you like a small-scale example of, you know, an easy example where you can see that you can manipulate things quite easily. This is just the mixture model where you put different priors on the number of mixture components. And this is sort of a well-known example of where the prior is really influential in the posterior inferences you will actually draw. So plain English, what we see here is that Bayesian machine learning is not necessarily a reliable inferential device. And so that's why these people started sort of independently of one another and not really as a coherent unit to come up with ideas of how we could perhaps remedy this issue. And
Quickly flash back that slide. So it's not just surprise, it's the model.
yeah, so in this instance, the only thing you're changing between the two plots is the prior. But indeed, it is both the model and the data as well, actually, that things are saved. Yeah. And so, yeah, people started, you know, thinking about this, and I'll collectively call this set of ideas post-Bayesian. And so to understand really what I think is a good framework to understand what these post-Bayesian machine learning procedures do is they really look at the Bayes posterior as simply one possible belief update in the space of belief updates. And if we want to be a bit more formal about what a belief update is, we could write down the set of functions, right, which take a prior from the space of priors, that take some data set from the space of data, and potentially some hyperparameters that additionally influence your belief updates, and then they map back into the same space from which you took your prior, and that's your posterior. And so a very simple example of this, which no longer follows Bayes' rule, is actually the power posterior, which some of you may know as the cold posterior, others might know it as the fractional posterior, has lots of names. And essentially you just raise the likelihood to some power, and you end up with this thing. And normally people do this in order to address the misspecification of the model. And I would credit this to Peter Grunwald, even though obviously he didn't invent this, but I would say he's the one who very strongly pushed for this as an inferential device. If you're not happy with this and you kind of want to do something that sort of is a larger space of possible belief updates, because this is obviously quite limiting just to raise the likelihood to a power, what you could do instead is essentially compute a Gibbs posterior. And so that was, I think, mostly advocated for in 2016 by Posterior, Holmes, and Walker. Again, I'm not claiming they invented the Gibbs measure, but what I am saying is they made the point that if you choose a loss function that connects your data to some parameter and you exponentiate the negative loss, you can call that a pseudo likelihood if you want. It has nothing to do with a likelihood, so I don't like that term, but you could call it that, and you can compute something that looks a bit like a posterior. And so I should mention that this is roughly around the time when I got into the field, because it's roughly around the time when I started my PhD. And so a lot of the work I did initially was related to these kind of objects. And then in 2019, really, we figured that we can actually generalize this even further into something that I would call the optimization-centric generalization of Bayesian inference. And this may look a bit weird, but essentially what it is, it's a form of generalized elbow. And the motivation for this is that you can rewrite any Gibbs measure in this form, right? You can rewrite it essentially as the elbow, where you're taking the minimum over the space of all probability measures on the parameter space. And then all you're observing here is there's sort of three components: the loss, which we're already playing with, and then there is a regularizer with respect to the prior, and then there's a space over which you can take this minimum. So essentially what we're going to do here is play with all three. And the rationale behind this is you can address model misspecification through the loss, and we'll see later in the talk how this works. You can address misspecification of the prior to some degree, at least, by choosing a more robust regularizer. And you can address the computational concerns if people have done, forever, essentially by using a variational approach. If you minimize this over, for example, a parametric subset of distributions, then this just recovers something that looks a lot like variational inference. So you kind of have three different knobs that you can tune here to sort of help you overcome whichever assumption is problematic for you. Of course.
So the model will specify this basically means your data is in the model class.
Yes, or approximately, yeah.
Well specified. I guess you can talk about that. Kind of, what is well specified?
Yeah, so this is really, so it doesn't, like, there is obviously no true prior because you actually assume that there is a true parameter, right? So it doesn't make sense to introduce randomness. What it means is your true beliefs about the world can be written down as a random variable, and you have the faculty to write that down in a probability distribution. Right, so if I ask you to write down your prior over the height of people in this room, you would be able to write me down some density function that represents that belief.
So by well specified, you mean experts can encode their beliefs in this formula? So yeah, so the thing is, you don't even need to be an expert, but you need to be able to write your stuff down as a density function, and it would have to be in relation to what you actually believe to be true. I thought that you don't have to be an expert. You get really badly. Whatever
yeah.
you have, you can encode.
Yeah. That's really what this says. Yeah, it relates actually to the Savage axioms. So this comes from the motivation for Bayesian inference through how rational decision makers make decisions. And so a rational decision maker, basically, their preferences should be expressible through priors. We can at the end of the talk, I have like some additional slides in the back where I explain this in a bit more detail. Okay. Right, so this is essentially the tapestry that I'm going to talk about today. Starting with the Bayes posterior, you can sort of increasingly generalize this, and we'll talk about all of these objects over the course of the talk. Of course. Sorry, can you speak up? I'm a bit bad of hearing. What makes it?
Makes us move.
What makes us move?
Yeah. You are saying that the posterior is one of the and I'm saying that makes me having other posteriors.
Oh, I see. Well, it depends on what kind of generalization of the posterior you look at, right? So for example, in this orange generalization, the way you move in this radius is through this scalar quantity. Once you look at this green space, you're moving by varying the loss function that you use to connect the data to the parameter. And then once you're looking at this bigger set, there's a whole lot of variables you do. So depending very much on which of these frameworks you use to choose a post-Bayesian algorithm, you operate in very different sets, if that makes sense.
So is it realistic or like computationally feasible to like use all these and fine tune for like large models, all these parameters like lambda and everything?
Yeah, so this is an excellent question. Generally, no, right? So this is part of problems that need addressing in this space. So it's like one of my last slides. All of this is great, but also we don't really yet know. We know for some parameters, but for some others, it's much more difficult. So it really depends, right? Because this is a big space, the answer is that it depends. Okay, so before I move to sort of, some of the theory, I just wanted to mention some success stories of like work that has come out of doing these kind of, or working on these kind of post-Bayesian machine learning techniques. So for example, we have this. Then currently we're actually working with the Met Office and try and help them to implement a version of the algorithm we proposed therein to sort of implement wind farm placement algorithms. So they're trying to figure out what's the most efficient way of implementing wind farms that requires really expensive simulations. And what's elegant about the approach that we proposed in this paper, and I'm not going to actually talk about that approach today, but what's elegant about it is that it allows you to compute things really quickly. And similarly, so we just have an ICML paper accepted as a spotlight. My student Matthias is actually going to present it if you're there in a few weeks. And he's currently actually implementing this for a startup that some of you might know. If you know Jacob, he used to be at UCL, and he started this company where they're trying to do material science. And they're using a Bayesian optimization algorithm that uses post-Bayesian techniques under the hood. Okay, anyway, so this is sort of the preamble ended. And what I'm going to do now is sort of break up the talk into 3 parts where I'm talking about different aspects of this tapestry that I've contributed to. And sort of the first one is foundational. So this relates to sort of, just cold posteriors and Gibbs measures. And it mostly relates to model misspecification, because this is really what people started to look at the beginning. And then in the second part, I'm going to look at sort of the state of the art, which realized that actually just looking at misspecification isn't enough, because what you end up with is things that are robust and not computable. So very much to your point, how we can design these objects with computation in mind. So sort of computation first generalizations. And the last part, I'm going to look a bit at the future, which is very uncertain, I would say, but very exciting. There's lots of stuff to do. And this is really the idea of addressing all of these assumptions in turn, depending on which one you want to relax. Before I move on, here's just like a selection of collaborators that I have to thank immensely for making this work possible. Nobody does research alone. These are my heroes. I just wanted to mention them at one point today. Look them up. They're all fantastic. Okay, so throughout the talk, so that you can sort of, if you get lost, to orient yourself, at the top left corner, you always see what kind of assumptions we're currently tackling, right? So I'm crossing out the assumption number 1 here, because that's the one we're going to tackle in the first part of the talk. And similarly, at the top right, you'll see which part of the talk we're currently at, right? So foundation, state of the art, and the future. And so for the foundational questions, we're going to ask 3 questions: whether tuning the lambda parameter can actually improve robustness, what kind of property we need on the loss to get a robust generalized base posterior or Gibbs measure, and how we should choose or design these losses in general. And so for the first question, the motivation for this really is, okay, so just a brief reminder what the cold posterior looks like. But the motivation for this really is that there's sort of 2 separate literatures, I would say, so sort of more from classical stats, and then also more core machine learning, that have both looked at this question and kind of reached similar conclusions. So I could have put like some quotes on here from these 2 different communities. And essentially, the claim is always that tuning this parameter lambda can deliver you more robust predictions. And so, for example, there's this famous paper from 2020 where the question was, is there actually any point to doing Bayesian deep learning? Or it's called it talks about what's called the cold posterior effect. And essentially, this is the effect that as you increase lambda in Bayesian deep learning, you actually improve your outcomes. And so that there was a really big, I think the paper got like a lot of traction at the time, but it's not really clear.
Alpha, aren't you just going to optimization?
Sorry?
If you increase alpha sufficiently, aren't you just going to
Yes,
maximum likelihood?
precisely. Yeah, that's exactly what's happening. And you're teasing the results that I'm going to show. Yeah. It's really unclear why this should be true, because the only thing you're tuning here is the trade-off between prior and the data. And if you put all your mass on the data, you're just going to recover the maximum likelihood estimate. And so the question we asked is, well, what if we chose this value of lambda in an optimal way, right? So if I'm trying to make it so that I get the best possible prediction, could I tune this parameter lambda to minimize some kind of distance between the true data generating process, right, which is sort of the optimal predictive, and the predictive distribution that's induced by the lambda? And actually what we found was really weird. We found these kind of curves. So as you tune the lambda towards infinity, it flattens out. What's really interesting here is actually at the prior predictive, you're obviously the worst because you're just predicting from the prior. You haven't learned anything from the data yet. As you move towards the base posterior, things really improve, but then they just flatten out. And actually, they flatten out even before the base posterior. And depending on sort of the number of parameters and the number of data points you have, this sort of kink can happen really, really early on or really late. It really depends on the ratio of the number of observations to the number of parameters. And what this tells you is that there's sort of an infinite number of lambdas that actually all give you equally good predictions, because essentially posteriors aren't necessarily about predicting, they are about representing uncertainty of the parameter. This is essentially what's happening here. And so, yeah, you can prove this formally. So I'm not introducing any of the math because it's quite heavy notation. And this paper is forthcoming. If any of you are in Venice for ISBA, my PhD student Jan is going to present this work. But basically, the findings are that it's an ill-defined problem to try and tune this parameter to make your predictions optimal. You get a flat region of infinitely many lambdas that all give you the same predictive. And there's actually no advantage, as you've just said, over just choosing the point estimate, which is not great if you actually want to advocate for a Bayesian approach to the world. And so, yeah, the conclusion is that normally tuning this lambda will have no effect on the robustness.
So presumably you prove this in general for everything, or?
So no, there's some restrictions. So what we need to impose at the moment, I'm hoping that we can relax this. We need to impose that the maximum likelihood estimator converges to a point and that the posterior concentrates. And basically what you do is a triangle inequality, and then you get two terms that shrink. But what we find in practice actually is that these conditions are not necessary. We get a much faster convergence than the theory would predict, and B, we don't actually even need these requirements. It's quite a robust finding, which surprised us. But these are at the moment the conditions we're working with. This is why the work isn't finished, because we are not happy with the conditions yet. Okay, so the reason this happens is you're essentially predicting from something that's very close to the plug-in predictive extremely quickly. And that means that this cold posterior effect is actually not something that's specific to deep learning. It's a much more general phenomenon. What's specific in deep learning is basically just the ratio of observations to parameters. And this is why it shows up more drastically. It shows up for larger values of lambda than in sort of normal statistical scenarios. Okay, so we don't get robustness doing this, but the solution for robustness is actually to just instead look at this different generalization. Sorry.
What was the value of n that you considered?
In this particular instance, it looks the same for all possible values of n. I don't think I have it in the slides, but I think what I showed you was 100. So yeah.
Wait, but just to be clear, like Lee said, for large lambda, you're just looking like fire.
Sorry?
For large lambda, you're looking at like data ignoring the fire. Is that correct? For large lambda.
Yeah, you're increasingly ignoring the prior. Yeah. Which makes sense in deep learning.
Not just that, you're also sharpening that likelihood
Yes.
effect. So you're just concentrating on the mode.
Yeah, yes. You're doing ML. Then it's not because you're doing ML.
Yeah. Yeah.
You can think of easy cases, but that's probably bad. You have the right prior and 1D.
Yes. So exactly. If your prior is arbitrarily good and your data happen to be a really poor batch, then in fact this would be a bad idea. But essentially what the results show that we derive is that this doesn't happen with high probability. Okay, and so we can't get robustness through this, power or this cold posterior. So the question is whether we can do it through the loss. And so in this part, we're going to look at what kind of losses you need to choose to induce Gibbs measures or generalized base posteriors that provide robustness for you. And throughout, we'll basically consider a sort of very classical statistical setting, which is the Huber robustness. And what this basically means is it's due to a guy from the 60s called Huber. And what he proposed essentially to study as a sort of canonical way of assessing robustness is that the data generating distribution consists in two parts, one that you can explain really well with your model and which has size 1 minus epsilon, and then an epsilon-sized contamination distribution, which you cannot explain well with the model. And what you essentially want in this case is if you draw a sample from the contaminated distribution or the uncontaminated one, you want that your posteriors roughly draw the same conclusions, right? You don't want a very tiny fraction of the data to really bias your conclusions in one direction or the other. And so to sort of illustrate this, we're looking at US stock volatility data from a normal year and from the year when the financial crash happened. And obviously, a lot of financial institutions went under, so their volatility in their stock was really high. So you can see that a Gaussian is sort of like a reasonable enough model in 1 year, but then no longer in the next year. And when you just fit a standard Bayesian distribution here, or if you fit a distribution with a standard Bayesian algorithm, I should say, you're kind of over-smoothing to this contamination. And it's maybe not something you want. And the kind of problem we're trying to target here is that you're basically ignoring this contamination. You're happy to take the loss on this bit, and you're just trying to fit the rest of the data really well. So this is the kind of robustness we will be considering.
What is this method? The name of this method, or this
Which
kind of
Huber robustness?
Huber robustness.
Huber. So he's a, I believe, Austrian man. Huber. He has a couple of really famous books on robust statistics in the 60s. There is one from the 90s that's more readable. It's actually really good. I really enjoy reading it. It's very clear, the early chapters in particular. Okay, so that's the setting, right? We have these two posteriors, and what we essentially want for robustness is that the distance between the contaminated and uncontaminated posterior is small. And when we say small, we mean that there's some kind of constant, and then the effect of the contamination is at most linear. So for example, we don't want exponential growth in epsilon. The problem with this statement for robustness is now we can play with a constant and we can make this constant arbitrarily large. So what we actually want is we want some sort of set of possible contaminations, and then we want to look at the worst case, and we want to make sure that that worst case is still bounded. So this is normally how you approach this kind of problem. And for a long time, people were like arguing about this distance, and the problem was people came up with really elegant solutions, but they were elegant on paper. You couldn't really work with them. And so what we did in 2022 in a JSSB paper is we kind of came up with something that was simple enough, but powerful enough for you to actually do useful robustness analysis. And all you're doing is you're looking at the supremum distance of the densities between the contaminated and uncontaminated distributions, right? So you're looking at the worst parameter value where they are the most different. And if you're doing this, what it allows you to do is to formally reduce this problem to the loss itself. So what you need to do in the end is look at what I would call the sensitivity of the loss to contamination, which is just this derivative. So this is basically just a simple sensitivity analysis of the loss function, which is really important because this distance is defined on the space of measures. So that's really intractable and terrible. This is a really simple object. And then you can essentially formally show that your posterior is going to be robust if this thing in a certain way is robust as well. If you're interested in the detail, I have like some more slides in the back. Basically, if you integrate this sensitivity with respect to the prior, that needs to be bounded. No. Okay, so we've seen how we can, in principle, choose robust losses, but what we haven't actually discussed is how, in practice, you would choose these losses. I mean, where do these losses come from, right? And so the answer to this question is discrepancies or divergences. So the motivation is you can always write the standard base posterior through the negative log likelihood, and actually, it turns out that this is essentially an approximation to the Kullback-Leibler divergence. Now, it's well known that the Kullback-Leibler divergence itself is not a robust divergence, and so therefore it's not robust to model misspecification. But you can flip this on its head and say, well, what if I choose a robust divergence? And when I say robust, again, I mean that essentially, if you look at the divergence between the model and the contaminated versus the divergence between the uncontaminated model and so the uncontaminated data and your model, they're roughly the same. Well, when you do this and you can derive a loss from that, essentially the resulting loss will be robust. Okay, so this is not a formal statement, but this is how in practice you go about choosing these losses.
Do you investigate that text the balance of the transport, or did it come to
Wasserstein distances and so on?
Yeah, actually, the unbalanced variance is known to be robust to this kind of outlier.
Yeah, so there you run into computational problems. Like computing the Wasserstein distance is a bit too much for this stuff. But in principle, yes. I haven't looked at it, but some people have looked at it, not in this setting, but for parameter estimation.
It's not really Wasserstein, it's really unbalanced.
Okay.
Unbalanced
I don't think I know that stuff, so that would be interesting to actually read up on. And so some examples of these kind of losses or divergences that cropped up around 2018. I mean, they're older, but that's when they really became important in this context, are the beta divergence and the gamma divergence. And they actually look very similar. I haven't written them out for here. What's important about them, though, is they both recover the negative log likelihood as a limiting case. And that's attractive because you can still recover the Bayes rule as a limiting case. And essentially what this does is for small values of gamma or beta, you're essentially doing Bayesian inference after excluding the outliers. That's kind of the practical effect this has. And that's obviously very attractive. And so this was quite popular at the time. And one of the things we did is apply this to deep Gaussian processes. Now, in deep Gaussian processes, you have a huge computational burden because you're basically stacking Gaussian processes. So you're multiplying your computational concerns with Gaussian processes each time you do this. So the number of hidden layers here are the number of stacked Gaussian processes. So this is a hierarchical model. If you only have one hidden layer, what you can see here is that just using a loss function that corresponds to a post-Bayesian procedure makes things much better already in terms of prediction. And in fact, this trend continues. So if you increase to 2 layers, you can see actually you're 1 layer better just by switching to a post-Bayesian procedure. And this trend continues all the way to 3 layers. And so basically this means, this is, by the way, this is very simple to do. You just change like literally 1 line of code. So even I can do this and I'm not a great programmer. And what this tells you here is you can actually make significant computational gains at the same, with the same test error without a lot of effort. So you might wonder, why aren't these divergences more popular? Why don't you see them everywhere if they're so fantastic? There's a good reason for this. And the reason is that generally they're not tractable. So they work in the context of a deep Gaussian process, because in the deep Gaussian process, you're essentially using a Gaussian likelihood. Outside of a few exponential families, they involve an integral that's not tractable. And so that's the reason that people don't use them that often, because in this case now, you need to draw S samples from your likelihood model to approximate these integrals. And this is terrible. Like, this is not very tractable. And in fact, so here you can see how terrible it is. So here the exact posterior is sort of the black line or the dotted line. And we're computing an approximation where we actually sample 100 times more from the model than we have observations. And in this case, it's 25 observations before you ask. So we sample 100 times more from the model, and you can see the approximation is still absolutely terrible. And this led us to investigate this phenomenon in a recent preprint with David Frazier from Monash. And we basically find these divergences are terrible. Like, you need to scale them at least quadratically to maintain the approximation quality that they provide in the number of data points. Okay, so to summarize the first part, right? We saw that improving robustness is not possible by tuning the power or temperature in a cold posterior, and that you should probably work with the loss instead. When we looked at robust losses, we saw that they're robust. Well, sorry, they produce a robust posterior whenever they themselves are robust. And the question of how we should design losses was choosing robust divergences and then making them into a loss. But on the last slide, we also saw that there's a real trade-off here between robustness and tractability, and there seems to be this friction. I mean, robustness is no good if we can't compute, right? So this leads us to the second part, which is where we're addressing this point. So now, as you can see, we're tackling 2 assumptions at once. We're trying to get rid of model misspecification while maintaining computability. And
question?
Yeah.
Do you always want to throw out outliers?
Do I always want to throw them out? It really depends on what kind of inference problem you're trying to solve, right? So sometimes outliers are actually just something you should model explicitly. I'm not making the argument that you always throw away outliers, but sometimes people specify a model to the best of their abilities, and then you want to make sure that you can probably explain 95% of the data well, rather than have a lot of mass in regions where there isn't actually anything. And in high dimensions, this is particularly important. So like all the examples you see are 1D, because that's easier to show. But in 100 dimensions, essentially every observation becomes almost an outlier. So this is a really pervasive problem in high dimensions. Okay, so in the... Sorry?
These methods generally work.
It depends on the exact methods. So the ones I'm going to present here, they're computationally a bit more expensive, but they are still tractable in high dimensions. They definitely work, yeah. Okay, so the problem we've identified, right? So there seems to be a contradiction between the desire for robustness and tractability in the first part. So now we're going to ask, can we design losses that are tractable and robust? And again, all of this will happen in the framework of Gibbs measures or generalized Bayes posteriors. And so we actually going to look at a setting that you might be familiar with, which is a setting of unnormalized likelihoods, where people have a very similar problem. So unnormalized likelihoods, you have a unnormalized density. So it's not a probability density, but it is a density, which you can evaluate. And you have a normalizer, so an integral, which you cannot evaluate. And so one solution, which is very much the same solution that we saw with the losses, is you can just brute force the thing. So you sample from this density. This assumes you can sample from the density. And then you approximate the thing with an average. But we don't want that. We've already decided we don't want that. So what we can do instead is score matching, because we know that actually score matching is a method that you can use in this setting, and that's very attractive. So obviously score matching invented by Aapo Hirvonen, who was here. I think he invented it before he came here, but he's definitely refined the ideas while he was here. Okay, so suppose we're in the setting. The idea of score matching, just as a brief recap, is you can obviously evaluate, supposing the gradient exists, the gradient of the log unnormalized density. And through some easy maths that's fairly trivial to see, you can actually see that this is the exact same as looking at the gradient of the log of the intractable model. So since we have access to this, we also have access to this. And this is called the Hirvonen score. And once you have the Hirvonen score, the idea underlying score matching is, well, why don't I just match these Hirvonen scores? And if I'm lucky, that gives me a parameter that's sort of close to the data generating distribution, right? So I'm matching this to the score of the data generating measure. Now you're going to say, that's a bit crazy. Obviously, we don't have access to this data generating measure. Fortunately, integration by parts helps us out. And this should be an approximation sign because you need to approximate an expectation with an average as well. But basically what ends up happening is you get an expression that you can evaluate because it only depends on these scores. And that's going to be the loss we're using. But hang on, there's a problem. Score matching, which you can look at as a version of the Fisher divergence, actually isn't robust because the Fisher divergence isn't robust. So we've just gone on and on about robustness, and now we're going to use a loss that isn't robust. That doesn't seem particularly good. So what we're going to do instead is we're going to generalize this Fisher divergence in a way where we can make it robust. And the way to do this, and I'm sure some of you in the audience actually work on this, are Stein discrepancies. So I know that Arthur works on this a little bit. And Stein discrepancies can actually be made robust if you choose your Stein sets in a smart way. Or not the Stein sets, sorry, the Stein operators. And that then leads you to robust losses. Okay, so that's the strategy we're going to deploy. So in order to do this, let me quickly run through what Stein discrepancies actually look like. Again, I'm sorry for those of you who work on this, might be quite boring for you. But if you look at the distance between two expectations, what you're essentially doing is you're looking at the worst case between these expectations over some set of functions. And that set of functions really is the key here, because obviously the supremum in general will not be tractable. So you're doing a lot of smart things to make it tractable. The first of them is that you ensure that the second expectation here is always 0. So for any element in the set of functions, that expectation is 0. And you're treading a really fine line here because you need to make that set big enough for this supremum to retain meaning, but you need to make it small enough that the second expectation is always 0. The second ingredient you need is you need to make sure that actually it has a closed form solution. So there's a maximizing function for which you can essentially rewrite this expectation over F star. And this is something which in our case we do with weighted Langevin Stein operators. And Stein sets are either RKHS or L2 and C1. And then what this leads to is essentially a loss function that is now tractable. And it depends, crucially, on theta only through this expression. So it's a weight multiplied with the Hirvonen score. And this weight gives you robustness, and the Hirvonen score can be evaluated. Now, the robustness is essentially, what it essentially does is if the Hirvonen score is really, really big, that means there's probably an outlier there. So you're weighing it down. So the weight goes down if the Hirvonen score becomes arbitrarily large. Okay, so this gives you a loss that's both robust and tractable. Now, the question is this actually useful? So when we look at this and we compare it with the base posterior, right, in terms of robustness, we're definitely doing our job here. This is now robust, provably. With intractable likelihoods, it's actually faster to compute because you don't need access to the normalization constant, which is a real headache in a standard Bayesian posterior. If your likelihood is tractable, then basically both require you to run some kind of MCMC algorithm, or you need to approximate variation or whatever, but roughly the computational cost will be equal. And so the only possible scenario where the base posterior could be faster is if we have some sort of conjugate likelihood and prior combination. It turns out, no, because we can do something very similar with these Stein discrepancies. So what's very cool is for any exponential family, and this includes exponential families that don't have tractable normalization constants, which involves a lot of graphical models, for example. But for any exponential family member, you actually get this quadratic square loss, sorry, the square loss here on the right-hand side. And the reason this is very cool is if you take the negative of this loss and take it to the exponential, then this on the right-hand side looks suspiciously like a Gaussian, right? And what that tells us is we do actually have a conjugate prior. For any exponential family that we plug into the Stein discrepancy, the Gaussian is the conjugate prior. Or if theta doesn't live on the entire Euclidean space, it's the truncated Gaussian. And so in general, we actually now have closed form solutions for these post-Bayesian procedures. So that means they're computationally extremely efficient. And this is true, again, even if your likelihood is intractable. And so that means even in a scenario where the base posterior has a closed form, we are as fast or sometimes faster. And the sometimes faster, again, that's when your exponential family is intractable. And that's a really interesting scenario, actually, because it means that the base posterior would be doubly intractable. So there are two layers of intractability, and you have yours in closed form. So a really important special case. What's great about this is you now have something that essentially works as though you had sufficient statistics. Sorry.
So is what you have done that actually putting out on some space?
Have I put the Gaussian on?
On some other space.
On some other space.
Your first side.
Mm-hmm.
You write that as Gaussian.
So you haven't changed the parameter space. I'm not sure I understand the question. Oh, are you asking, have I just designed a different likelihood function? No. So, okay. So the answer for this is no. And the reason, if I understand your question correctly, the answer is no, because this isn't a likelihood function. So this is itself essentially an intractable likelihood, if you want. So that's why it's not quite the same. If that makes sense. But obviously, we're happy to ignore the intractable normalization constant. So we're kind of getting out of jail for free in that sense, right? Okay, so we essentially have applied this in various contexts. So you can apply this to Gaussian processes, to graphical modeling and change points. But one application I want to show you where these closed forms are really cool are online problems. And I'm going to show you a Kalman filtering example where basically you have, some kind of measurement error that's polluted or is imprecise. And because the standard Kalman filter relies on Gaussianity, if you don't make it robust, which people often don't do because it often incurs a computational burden, you will end up with something that or that should be moving anyways, is the observation. And the inferred latent space is sort of the line. And you can see if there are outliers, the standard Kalman filter really struggles with sort of recovering from this. This is not true if you use these robustified versions of the algorithm. And that's very cool. You can actually suddenly use something in an online setting. Okay, so the question we asked is whether we can design losses that are both robust and tractable. And Stein discrepancies were one of the answers. You can also use weighted likelihoods, which I've not really explained. Okay, so the last part, and I think I'm running out of time a bit, so I'll speed through this. But in the last part, we're going to look at, what I would consider probably the next step along this journey, where we're trying to abandon all of these assumptions, hopefully, or at least relax them. And the main thing here really is that you want to additionally look at the relaxation of the prior being well specified, because this is really the main gain you get from using this generalization, because you can now play around with the regularizer. So just as a quick reminder, right, we looked at this earlier and we saw you can address 3 problems with 3 different components in this problem. You can manipulate the loss, and we've done this already today to get robustness to model misspecification. You can manipulate the divergence, hopefully to get you robustness to the prior, and you can manipulate the set to give you some form of relaxation of the computational burden required. And to convince you that it's actually useful to play around with the divergence, here's sort of an example where we did this with a Bayesian deep learning example. This grading here gives you the uncertainty implied by the predictions of the neural network. And we're projecting along this diagonal axis onto this X and Y space. So I think this is more informative. So probably just look at this. So here we're running like a full Bayesian algorithm, which in practice is essentially never feasible, right? We're running HMC. We're looking at the regions where we don't have any data. So these dots are the data points, and you can see we essentially only observe them in 2 regions. And what you basically want your neural network to do is to say, oh, I'm uncertain about this in-between space, right? That's what you would want. And that's what actually happens with standard Bayes rule. It just happens to be computationally mostly infeasible to do this. What people do instead in practice is, mean field variational inference schemes or Monte Carlo dropout. Either of these will lead to a complete collapse of uncertainty between these 2 point clouds, which is not great. And so what we really want is something that behaves a bit like standard Bayes, but at the computational cost of mean field variational inference. And unsurprisingly, you can actually achieve this. In this case, we do actually use the Wasserstein distance, because in this case, the prior is Gaussian, so this thing has a closed form, so it's not a computational problem. And what you end up with in this case is something where the uncertainty is perhaps more favorable, where it's something that you would probably prefer that over that in terms of the uncertainty that's implied. Okay, so there are also other problems with this that are interesting to think about. Once you write down this thing, right? So I've spoken about tackling this as a variational problem, and it's kind of obvious that you can do this, but it's unclear in general how you would compute these distributions if that set Q you're optimizing over is not parametric. So what if I want to actually optimize this over the space of all probability distributions? And actually, the algorithmic solution to this is Wasserstein gradient descent, which you can think of as an infinite dimensional gradient descent on the space of measures that have finite second modes. And that's something we implemented in a NeurIPS oral last year. And when you do this, this is essentially a strictly convex functional if this regularizer is strictly convex in Q. And that's why it works. It's basically just convex optimization. Just happens to be in an infinite dimensional space. And you implement it through an interacting particle system. One of the side effects of this is that you now have a sampling algorithm that doesn't even need to know its target. So I'm not aware of any other sampling algorithm that functions this way, but I'm also not an expert on sampling. So this may be a claim that's wrong. I think it's the first of its kind. So we have a sampler where you only need to state the objective, and you can compute the posterior implied by the objective by essentially doing infinite dimensional gradient descent. So that's kind of cute. Another little bonus, and we'll come back to this in a little bit, is that this algorithm sheds light on a lot of the things that motivate me for doing my research. And it's kind of a morality tale that I'll close the talk on. Before I close the talk, I wanted to give like a few high-level cliff notes. Sorry, are you raising? I wanted to give a few high-level cliff notes on unresolved issues, because there's loads of them. I don't want to bore you with that for too long, because I never think it's interesting to just list problems. But I just want to provoke some thoughts, right? So obviously, we've introduced this D, but we have no idea how to choose it. In fact, we don't even know how we should think about robustness of the prior with this divergence. We haven't mathematically conceptualized this yet. And that's because these objects are extremely difficult to work with. We also saw, there's some conjugate posteriors, which raises the question, can we actually characterize the set of all these conjugate post-Bayesian mechanisms? Is that possible? Because that would be quite interesting if we could say we can explore that space more thoroughly. Oh yeah, I already mentioned this. We don't know how to formalize this prior robustness. There are some formalizations of prior robustness from James Berger and so forth from the 80s, but they're very, very different. It's not the kind of robustness we care about here. It's also really not clear, right, how we should choose between different post-Bayesian methods. I mean, I said we don't know how to choose the divergence, but this thing has 3 components we can play with, and there are completely different frameworks, like the martingale posterior, for example, that I haven't even spoken about today, that have completely different components to play with. And we really don't know how to navigate this space of possible belief updates and how we should think about posterior selection. Right? We know how to think about model selection. We don't know how to think about posterior selection. So there's a whole headache of problems. We don't know basic asymptotics. I tried to derive the asymptotics for this during my PhD. I ended up being able to show that they concentrate to a point mass, but we don't have rates. And the reason, again, is because you don't generally get closed forms for these objects. So you need to rely on something called gamma convergence, which is really painful to work with. Yeah, so there's lots of open questions, but rather than expanding on them, I'll sort of end with a little morality tale to explain why I think we should care about this line of research. Okay, so remember I said we can apply the Wasserstein gradient flow on these objectives, and actually it gives us an algorithm that allows us to compute posteriors of this form. So actually for the special case of cold posteriors or base posteriors, the resulting algorithm is really well known because it's just a Langevin diffusion, and you can formally show that essentially implementing the Wasserstein gradient flow gives you the Langevin diffusion. And this converges to a well-defined define density, which is just going to be, you know, the power posterior or the cold posterior. Now, if we take lambda all the way to infinity, which basically means now we're in the setting where we're ignoring the prior completely, you can actually show that you're recovering deep ensembles. So this limiting case is exactly equal to the deep ensemble, and that's exactly equal to the Wasserstein gradient flow on this objective. But as you can see, I mean, these are completely different objects, right? One of them is a density, takes a prior into account. The other one is actually a completely discrete measure. There's no prior influence here. So we all agree these are completely different algorithms, they're completely different objectives, right? Well, there's this paper that's been cited more than 650 times, which claims they're the same. It's obviously wrong, right? We've just seen that they're literally not the same. And so for me, that's really great because it motivates why I do the research I do. Right? For me, the reason that they've got this wrong in this paper is that in practice, orthodox Bayesian machine learning has already been abandoned, right? Like, so practitioners that work with deep learning, they don't really care about the foundations of Bayesian machine learning. They don't care about the foundations of Bayesianism. They want something that works. And so they do something that has a Bayesian flavor, but is not really following orthodox Bayesianism. And so, as you know, as an example, is these deep ensembles, which are now often referred to as a Bayesian deep learning algorithm. Deep ensembles, as we saw, they have no prior regularizer. They are discrete. A base posterior is a density, and it has a prior, right? And fundamentally, the reason why this happens is, as a field, we don't pay enough attention to the fact that actually orthodox Bayesianism doesn't serve us well, and so we need to go beyond that. But we don't have the language for talking about that. We don't have the mathematical grammar, and that's really what I want to work on. And I think it's important because if we don't have this mathematical language, then this leads us to making statements and conclusions that are just incorrect, like the statement you saw on the last slide. And so with that, I want to come to an end. I have some of the references and the reminder of the structure on here. And I also want to highlight my two PhD students, Matthias and Jan, who are actually both here at UCL. So you can meet them at UCL, or if you're ICML, you can catch up with Matthias, who's going to present hopefully 2 of our papers there. Both of which actually we talked about today. So it's the Kalman filtering paper and it's the robust Gaussian process paper. And Jan is going to present the first work I showed on tuning the lambda operator. Anyways, thank you very much for your time and your attention. And again, for abdicating the one summer day in London that we'll get. I really appreciate your time. And if you have any questions, I'll be glad to stick around afterwards as well.
In the first part of the presentation, how do you define an outlier?
How I define an outlier? This is a really good question. Outliers are always relative to the model you posit, right? So if you take a Gaussian model versus, let's say, a Cauchy model, an outlier doesn't really make sense in a Cauchy model, ever. But in a Gaussian model, an outlier makes sense. But it's always defined relative to the model class you're actually considering. Okay. I don't know, it's a good question. It has a very complicated answer. So I can't give you like a very brief rundown. But I think it's a very important question. People don't think about that enough, I think, what they mean with an outlier. It's very obvious when you have a Gaussian distribution. It's not obvious, for example, if you look at graphical models, right? If I look at my sample is an entire graphical model, what's an outlier? The distance I should use to compare different graphical models is no longer so obvious.
But then when you work out the robustness,
yeah, so the reason,
how do you?
Yeah, so the reason this works is basically when you work with likelihoods, you evaluate the likelihood of a data point. So anything that has an extremely small likelihood, you can think of as an outlier, right? So if I give you 2 bumps that are separated and there's nothing in the middle, for example, the density of this point for a parametrization that would imply this model is also going to be very low. So the moment I have a likelihood function, that's why I'm saying it depends on the model, and actually it depends on the particular parametrization of your model, right? But if you have a parametrization of the model that implies 2 bumps and you're observing a data point here, the likelihood of that data point under that parametrization is very low. So even though it's sort of like on the inside between the 2 bumps, it's still an outlier, if that makes sense.
It makes sense.
So yeah, I would think of outliers in terms of the densities they imply.
Use Cuba for generalization Cuba, and then
for what?
Like when defining outliers, like because I feel like a lot of this comes down to this idea that somehow the data that's not from the distribution we're interested in is somehow really different, and so that's why you made this example about the Gauss. The idea that you clearly see this tails of the Gauss decay exponentially, but like Cuba's definition is quite appealing as a starting point because because even though there's only one contaminating distribution, it kicks the ball down the road, because it could be that the other distribution is actually remarkably similar to the one that we're interested in. But like, I guess that when you're using experiments, right?
I'm not sure I completely understand the question.
Well, because you were talking about like what is an outlier.
Yeah.
And for me, I think the most straightforward way of thinking about an outlier is just to use the Cuban definition of, well, this is an outlier, it's come from a different distribution. So these data points came from distribution A, and if this one came from a different distribution, then in my view, that is an outlier.
Right. I mean, that's one way of thinking about it as well. Yeah.
And like then subsets of those cases.
So
will be sufficiently different.
Yeah. So the issue with this is, right, the Huber representation isn't unique. So if I give you a model and a different, like if I give you Q epsilon and Q0, there's different ways you can connect them. It doesn't necessarily uniquely define the C. So that's the issue with that. But I agree with this.
I think the story you mentioned at the beginning about domain experts. In your mode of that usually is when you, not that you don't have a domain expert, but that you have more than one parameter, right? You have, and it's not even data dimension parameter, but something like that.
Yeah.
You can't do this distinction because you can't get into the dependence of this parameter. So how would you address that?
It's a good question, right? This is obviously a continuum, right? Like I'm drawing this binary distinction. We're never in that world. I mean, there's never a perfect Bayesian analysis of any phenomenon, and there's never this perfect Bayesian machine learning analysis of a problem. There are shades of differences. And I think my work can have a place also when you're more on the statistical side. And it really depends on the specific problem you're looking at. So like some of the graphical modeling we did in this KSD base paper, for example, looks at cell communication, like between different proteins and their interactions, where you have exactly this problem. Like you have a lot of parameters, you don't really know how you should specify them. And so the model actually becomes sufficiently complicated that you can write one down as an expert, but even as an expert, you don't really, like as a biologist, don't really know if this works. And so this is not an example about the prior, it's an example about the model, but I think the story is the same, where you are kind of closer to Bayesian statistics, but you're not really in this sort of idealized setting either. And so I think a lot of Bayesian statistics is also shifting more in the direction of how Bayesian machine learning now operates. So I'm not really answering your question, I realize, because I don't have a good answer. My answer is probably the problem is more generic. I just left out, I don't want to get into the weeds of when you should apply this in border cases, because it's easier to get into fights. So I'm going to pick an extreme case. Yeah.
Like any way you apply this to that problem.
Sorry, so you need to ask the question again. So someone pays me a lot of money. I got lost.
Yeah. Can't draw them into a nice graph.
Mm-hmm.
And what some you don't know how to do this. I mean, you would like try to shoehorn your approach to that.
So the problem is the problem you're describing is we have priors, but we're not certain about them.
It's like you try a prior, you put independent priors in a parameter that
yeah.
Like you do what I would do in that situation.
Yeah.
Based.
Yeah.
With systematic. So that's like the biggest problem.
Yeah. No, I agree. I agree with this. If you don't have, so things you don't even need a good prior necessarily. Like sometimes this Bayesian deep learning stuff can work really well because it regularizes. So your prior can have this secondary effect of regularizing. But I agree with you in this specific setting, I'd probably not be convinced of a Bayesian approach. But what you might try, which I didn't have time to cover, is actually these martingale posteriors, because there you don't actually rely on a prior. They're kind of a fancy way of justifying why bootstrapping is. No, actually, that's Edwin Fong's work. So he got like the Savage Award for it last year. And basically, this work is born out of the idea, what if we could justify the bootstrap as a Bayesian procedure? And so if it gives you, as a Bayesian, it gives you permission to use the bootstrap and interpret. So it's the same algorithm, but the interpretation now changes. And now the uncertainty you get out of a bootstrap actually has, a Bayesian interpretation rather than a frequentist one. So I think in this specific scenario you're describing, I would recommend that because it's computationally feasible and it gets you out of the requirement of using a prior, really. That might be interesting. But yeah, I don't think this stuff is particularly suitable for that problem. Yeah.
So like earlier in the talk, kind of, am I right in saying you're kind of arguing that the way Bayesian machine learning is evolved is such that it doesn't really make sense to call it Bayesian anymore because they've deviated too far from these written principles. And a particular thing I picked up on was that, a lot of key part is this, or one of three things, is, you normally traditionally carefully specify the prior, and then now the updating of the belief corresponds to updating the probability that actually means something.
Mm-hmm.
Prior is just uninformative. There's this notion of like, what are we actually updating?
Yeah.
I suppose you could appeal to frequentist asymptotics of the posterior, but I got in light of that, what are your views on the benefits of this slightly more data-driven post-Bayesian regime over, let's say, a frequentist approach?
Right. Yeah. So it's a good question, right? So I would say you can still benefit from considering more than a singular model. Averaging is still probably a good thing. You may also just want some sort of uncertainty quantification in the sense that your predictive distribution means a different thing. You could also find yourself in a scenario where you do care about the parameters. Not all machine learning only cares about prediction. And once you care about parameter uncertainty, I think that's really when Bayesianism is at its best, right? So we don't, confidence intervals in sort of complicated machine learning models, you can't really derive them, right? Or even if you could, it would probably take you half a year. So on a practical level, I think you might be better off using a Bayesian framework, even if your prior is not great.
Okay.
So again, right, in practice, a lot of this is along sliding scales. I'm drawing these distinctions to make the argument, but I would have to see the specific problem we're talking about to make a firm recommendation. My view is that priors are surprisingly useful. So I didn't have time to show this, but you can actually look at the dual of this object, the differential dual. And what it shows you is that actually it shows you very exactly the influence that the prior has. It's just extremely technical, so I didn't put it on a slide. But you can think of it like the prior is essentially a cost function for you. So we're playing a game now. You're trying to minimize a loss function. I get to perturb your loss function, but I pay a price for perturbing the loss function. And the price I pay is higher in regions where your prior allocates more mass. And you can show this formally to be the case. And then the way essentially that cost function translates into the final cost I get charged depends on this regularizer. But it's always the same, regardless of the regularizer. And that's why priors can still have a purpose. So if you put your prior mass in regions of the parameter space where you're certain that this is the loss you actually care about, there's still a benefit. Yeah.
So you've got these three nodes. Is a particular algorithm uniquely defined by them, or can you basically end up with essentially the same algorithm with different combinations of changing loss, changing divergence? And so this is motivated by thinking about your deep ensemble, right? And so there the idea is one way to get to that is by saying I'm doing this discrete approximation to something I don't have a prior. But I think that at least the intuition that people are usually sort of espousing when they say that those are Bayesian-like is that they might arise effectively as samples from a posterior. There's going to be some weighting function that drove, some regularizer that drove your choice of that ensemble, which might be acting like a prior. And so can you rule out that interpretation by showing that it has this other one that says that it's discrete and fixed and has no prior?
So some ensembles, you can actually recover a special case of this. So in that paper, I didn't show it, but if your regularizer is not only the KL, but it's the KL plus the MMD, you still converge to something well-behaved, and you recover repulsive ensembles, where like people have designed these repulsive ensembles, right, where the individual particles push away from one another, and they use a kernel for this. And that's exactly the kernel that appears in the MMD that you use as a regularizer. So I'm not sure this answers your question, but there are various connections between this object and algorithms that are already in use, basically. It's kind of difficult sometimes to connect them, but we did connect that one algorithm to it. But for this algorithm, it's important to state that you do actually still get a well-defined density. So the repulsive ensemble, if you implement it correctly, has essentially a Langevin component. And so therefore, it still converges to a correct density. If you just So that it really depends on the individual algorithm. So there are other repulsive ensembles that correspond to not, so the one that works well, basically, and converges to a well-defined density is the KL plus the MMD. If you just use the MMD, you essentially get no randomness in your SDE. It's basically an ODE. And what that leads to is essentially, again, these discrete problems that you have with the deep ensemble as well. So the moment you have no KL regularizer, the SDE you evolve with the Wasserstein gradient flow becomes completely deterministic. And therefore, it can get stuck in subtle points and all this stuff. And so then you get all these suboptimal results. I'm not sure this answers your question.
Well, maybe unwinding that particular part of the question, rather than thinking about ensembles in particular. Go back to the original question, which is it the case, like, for a given, if I change L, right, is there a sense in which I can go back to the original likelihood and change D instead?
Oh, I see. That's your question.
Right. So to what extent is there a unique mapping between algorithms and particular choices?
Yes. Okay.
Because that becomes important for when you say this, it seems like it's important to know whether that's unique.
Yeah, absolutely. So there are some formalisms which, so we proposed this originally in a JMLR paper from 2022, and there's some formalisms you can implement. You cannot, in general, like these will have different effects, and one of the reasons is that one of them relates to the data and the other doesn't. So in order for them to give you sort of the same result, you need to be able to manipulate the data as well. So if you get to choose the loss, but also the data points, then you can recover the same algorithms. You know, like then I can fix let's say, a divergence, and you get to pick a loss to make it equal to whatever posterior you want, but you need to be able to choose the data for that under mild conditions. But generally, the answer is no. And that's because this object doesn't relate to the prior, it only relates to the data. And this object only relates to the prior, it doesn't relate to the data. So essentially that guarantees that there is this kind of trade-off where they don't end up computing the same thing. It's difficult to show these things with the level of rigor and formalism that I would want, but up to a point, we have been able to show that.
Great. Thank you.
Right. Well, thank you.